So in the next few videos, we'll focus a lot on CPU scheduling first, right? Again, the CPU scheduling is done by your short-term scheduler, as we have discussed in the previous videos, right? So if you notice, there is this, where are we? Okay, there is this short-term scheduler here, which decides which process in the ready queue should be picked up by my dispatcher to be given to the CPU, right? Or to be given the control of the CPU. So if you think about it, the task of the CPU scheduler or the short-term scheduler is to pick which of these processes in the ready queue should be given control of the CPU. That's what its task is. And what is its goal? What does it want to achieve? At the end of the day, it wants to maximize CPU utilization. It wants to maximize CPU utilization, right? It wants to ensure that the processes complete their execution as fast as possible. Okay, that's one way of thinking about it. And towards this goal of maximizing CPU utilization, there are many other metrics that we can think of. Now you might wonder, how do we measure this? Okay, there are a bunch of metrics or timings related to CPU scheduling. In this video, we'll learn about a bunch of these metrics. What do they mean? How do we compute them mathematically and things like that? In the next few videos, we'll dive deeper into CPU scheduling by actually learning multiple CPU scheduling algorithms and watch what each of these algorithms tries to achieve, right? So first and foremost, let's go and learn. Again, there are a bunch of metrics here. Okay, there are a bunch of time related metrics that we'll learn of one by one. The first one is called throughput. Again, we'll define throughput again, but in a very simple sense. What is a throughput, right? In simple English, throughput is the amount of work that you get done per unit time. Or in this case, it is basically the number of processes completed. You can think of it as number of processes completed. Okay, this is one way of thinking about it. It is a number of processes completed per unit time. So this unit time could be a second, could be a minute, could be an hour. We can pick any unit of time, right? So throughput basically says how many processes is my scheduler being able to complete. Again, the scheduler could try multiple algorithms. Again, in the previous video, we talked about something called as priority-based scheduling. Okay, again, there are multiple scheduling algorithms that we will learn of in the next few videos, right? Throughput basically, again, what does your short-term scheduler want? Your short-term scheduler want a high throughput because it wants to complete more processes in a given time, right? So given any process, imagine in a real system, I have multiple processes, right? I have P1, P2, P3. I could have n processes here, which are currently in the ready queue, right? So given all these processes, for every process, there is a time associated with it called the arrival time, sometimes also referred to as the admission time or the submission time. This is often written as AT, right? This is called the arrival time. Now, what is the arrival time? It is a time at which, look at this is the time at which, again, this is often referred to also as AI. If you're talking about a process PI has an arrival time AI. This is the time at which the process arrived into the ready queue. The process arrived, or the process was enqueued in the ready queue. I'll write RQ for short for ready queue, right? Then there is something called wait time, right? So wait time again is of multiple types. Okay, there is something called a CPU wait time. Okay, and there is also something called as IO wait time. Okay, a CPU wait time is the time that the process waits in the ready queue without being given a processor, without being assigned a processor or a CPU to work on, right? Without actually being assigned a processor to work on, right? So this is the wait time. So the wait time is often referred to as WT. Again, wait time could be of two types. There is a CPU wait time and there is an IO wait time, right? There is a CPU wait time and an IO wait time. Your short-term scheduler is mostly bothered about CPU wait time because it does not control your IO wait time. Look at this. Your short-term scheduler, again, if you go back to this diagram, your short-term scheduler cannot control how much time a device is blocked in the block queue or how much time a process is blocked in the event queue. It can't control all of that. But what it can control is how much time the process is waiting in the ready queue. Because if your STS or short-term scheduler is more efficient, it can schedule these processes much faster on the CPU, right? So if you think about it, The wait times could be either CPU wait time or IO wait time. And your short-term scheduler cares about reducing the CPU wait time, right? This is the time that it wants to reduce eventually. So CPU wait time is something that your STS wants to reduce or your CPU scheduler wants to reduce. Similarly, there is something called as service time or burst time or execution time, often referred to as XI. X stands for execution. This is the time duration for which a process is in the executing or running state. So process in running state. So the process is in running state, right? So right now what's happening, the process is in the running state. The process is assigned a processor or a CPU and it's now utilizing the CPU. It's also called as the execution time, service time or burst time. Okay, these terms are very important because we will keep using them a lot. Again, arrival time is often referred to as AI. Your service time or burst time is often referred to as XI or execution I. So given any process, I'll have an arrival time. Remember that arrival time is a property of a process. For every process, there is a unique arrival time. For every process also, there is a wait time associated with it, right? For every process also, there is a execution time or a burst time associated with it. Similarly, there is also a completion time associated with each process, right? So what is completion time? Completion time is the time at which a process completes, right? Very simple, very simple. Similarly, there is something called as IO burst wait time. This is the time in which, this is exactly this part. This is nothing but your IO wait time. This is the time during which the process is waiting for an IO event, for an input-output activity to happen. Okay, so this is wait time on IO. This is wait time spent on IO. Spent blocked on IO to be precise. Spent blocked on input-output. So just to give you an example here, imagine I have a process. Let's assume this is your time axis. Let's assume this is your time axis. Okay, let's assume this is my arrival time, AT. Okay, this is my completion time. Okay, this is the total. Again, this time is my arrival time. This is your time axis, right? So let's assume this is some 0. Okay, this is my complete time. If my complete time is, let's say, 10 or 10 seconds, then the total time it took for this process to complete is 10 minus, is basically your complete time minus arrival time for this process, which is 10 seconds. Now, in this whole duration, your process could be waiting. Look at this. This is wait time 1. This is the time in which the process is waiting in the ready queue, right? It's not blocked on any device. This is basically your CPU wait time. Look at this. This is nothing but your CPU wait time, right? So because this is nothing but your CPU wait time, because it is waiting in the ready queue, waiting for the short-term scheduler or the CPU scheduler to assign the CPU to it. After a period of time, it is assigned the CPU. Let's assume at this time it is assigned the CPU. Then there is a burst time associated with it. Okay, in this burst time, the process has control over the CPU and it's executing something. Now, after it has executed something, it could go into a block stage. Like, look at this. Here it's going into a block stage, waiting for some input. At this time, it is going into a block stage, waiting for some input output to happen. Here also there is a wait time, but this wait time is IO wait time. This is not your CPU wait time, because right now the process is in the device IO, waiting for some input or output to happen, before which, after which it can go back into ready state. Now, after it has finished the IO, it again goes into ready queue. Now the process goes into the ready queue, waiting for CPU again. Now this wait time T is or WT3, this wait time. Again, at this time, let's assume it goes into the ready queue because the IO is completed. Once it goes into the ready queue, it is again waiting for CPU, right? It's wait for CPU, then it is assigned CPU. Now again, I have burst time, right? In this time, I got the CPU control, right? After I got the CPU control, here the process got removed because some IO had to happen on this process. But there could be a high priority process or some other reason. Okay, there could be a system call, whatever it is. This process could be forced into wait again by forcing it into the ready queue. Here again, this is CPU wait time now. And after a while, after waiting in this ready queue for a while, I could be given again the control of CPU where I get again my burst time. And at the end of it, I complete. Okay, this is how a process, if you look at it from the time perspective, if this is the start time or the arrival time of the process and this is the complete time, during this whole life cycle of a process could go from one state to other state, and there are different times associated with time spent in each of the queues or on each of the devices. Like in this case, it is assigned the CPU because the process has control over the CPU. We call it burst time. right? So there is something called as a turnaround time. Turnaround time, very simply, is nothing but this whole time period. So for every process, there is a turnaround time. Turnaround time is complete time minus arrival time of a process. Okay, this whole time, in this case, let's assume we started 0 seconds, we completed 10 seconds. The turnaround time for this process is 10 seconds. Okay, again, these terms are very, very important because we'll keep encountering them when we design bunch of scheduling algorithms, right? So very, very important terms. There is also something called as a response time. Again, response time could come in multiple places in operating systems. Response time, broadly speaking, is the time it takes from the first time I make a request. For example, imagine if I'm in the ready queue. Okay, if I'm in the ready queue, which means I'm waiting for CPU to assign me, I'm waiting for the STS to assign me to the dispatcher so that the dispatcher can give control of the CPU, right? So when I'm in the ready queue, I'm waiting for the CPU, right? CPU is a resource. And here, if my process is in the ready queue, let's assume, okay, so let's write it this way. Suppose I have a process here, this process is in the ready queue. So what does it mean? It means I'm requesting control of the CPU. After some time, based on your STS algorithm and based on your dispatcher, after some time, my CPU is assigned to this. The first time my CPU is assigned to it is called the response. So first I'm requesting, look at this. How does it happen? The moment a process comes into the ready queue, it is requesting access. So there is a request response thing here. It is requesting access to the CPU. And then the STS has some algorithm. The dispatcher also will decide, so the STS decides when this process should be scheduled, gives control to the dispatcher. The dispatcher finally gives control of the CPU to this process. So there is a response happening, right? The first time the response happens, okay, this whole period is called the response time. The first time the response happens. So in this case, if you think about it, right now, see the moment my process arrives in the ready queue, I'm waiting for CPU. And at this point of time, if you notice at this point of time, I'm first time given control of the CPU. So this whole time period is my response time. Okay, again, response time is used in multiple places in operating systems and computer networks. Okay, again, there is something called a server response time in computer networks. Okay, so in a nutshell, response time is from the time you make the request for some resource to the first time the first response is made. Okay, look at this. The first time when I'm given the CPU is here, right? So only this time period should be counted in my response time. Okay, very simple here. Now let's go to some other definitions. Now there is something called as average turnaround time. Imagine if I have n processes. Okay, suppose my system has, let's say, P1, P2, P3, so on and so forth. I have n processes which are currently running. Now I want to measure what is the average turnaround time. That's very simple. What is the turnaround time for each process? Suppose for process I, what is the turnaround time? Completion time minus arrival time. We've used this terminology here, right? Look at this. The arrival time is the time at which the process arrives into the ready queue, the first time, right? Completion time is when the process completes. The process completes and it's terminating now, right? So now this is the TAT, the turnaround time of process I. Now what is the average turnaround time? It's a simple numerical average. Look at this. I'm summing so this is equal to 1 by n summation I, turnaround time of each process I. Average turnaround time is, if I have n processes, it is a simple average. So I equals to 1 to n. So it is a simple average, right? Or the mean of the turnaround time of each process. What is the turnaround time of each process? It is simply this, right? So average turnaround time is something that we also want to reduce, right? We want that, again, look at this. What all metrics we want to minimize? Look at this. So wait time, we want to surely minimize. IO wait time, the short-term scheduler does not control it. We want to increase the service time. Look at this. We want to increase the service time or the burst time or the execution time. The completion time, okay. What we want is, we want to minimize the turnaround time. We want to minimize the turnaround time, right? IO burst wait time, we don't control it because if the user does not enter, suppose imagine if I'm waiting on the keyboard input. If the user does not enter the input, the processor or the operating system or any of these algorithms, your short-term scheduler, long-term scheduler, none of them can do anything because the user is not giving the input. So they can't control whether something is efficient or not based on this, right? So that's one problem. So response time also we want it to be low because the first time you get response is something that we want it to be as, The first time I'm requesting for a resource like CPU, the first time I'm given control or the response of actually obtaining the control of the CPU or the resource itself, I want this time to be as short as possible, right? Similarly, there is a term, this is actually a slightly confusing term. This is often referred to as a weighted turnaround time. This is defined as this. Okay, what does this mean now? Look at this. What is this? This is the total time. This is your turnaround time, right? So what is this? This is your turnaround time. This is the total time from the arrival to the completion by time spent in execution. This is the time spent in execution of a process. Now, what should this be? Look at this. Look at this. What is this measuring? This is simply measuring how much time a process runs on the CPU. So this is measuring how much of the total time, because this is the total time that the process is spending between its arrival and completion. How much of the total time is spent on the CPU. Look at this. If I spend more time on the CPU, this whole value will reduce, right? This whole value will reduce, right? Because this number is increasing. So your weighted turnaround time is basically, it's a ratio of the total time we are spending with the total time we are spending executing. Okay. So for example, in this case, look at this. My xi will include this because this is the time I'm spending on the CPU, and it also include this because this is the time I'm spending on CPU. It will also include this because my total time that I'm spending on the CPU is this window plus this window plus this window. So that in the denominator, in the numerator it will be CT minus AT, or in other words CI minus AI, right? Very simple. Now let's look at this. There is something called as wait time of a process I. What is the wait time of a process I? Look at this. My completion minus arrival. Okay, this is the total time that we are spending. From this, if you submit, so this is the total time, right? This is my turnaround time if you think about it, right? This is my turnaround time. From the time of completion, if I subtract the time of arrival, I get the total time the process is alive. Okay. From that, if I subtract the amount of time the process is being executed, what do I get? I get the total wait time. Again, this wait can be CPU wait. It can be IO wait. It can be the wait itself. This WTI has both CPU weights and IO block weights. It could be either of them, right? But this is how we can define the total wait time of a process I, right? Very simple now. So similarly, we can also define average wait time across all the processes. What is this? This is the wait time of a process I. We just saw this, right? CI minus AI, total time minus time spent on the CPU. This is the total CPU wait time plus IO wait time, right? So now I can average it for each of them. If I have n processes, so what is this? This is nothing but 1 by n, summation I equals to 1 to n. This is wait time of I, simple average or mean average. This is also called as average wait time or wait time itself. Then there is this concept called as a schedule. Now what is a schedule? Okay, imagine if I have n processes. Imagine if I have n processes that are there. Now I could say that I want to execute P1 first, followed by P3, followed by P2, followed by P4, so on and so forth. I can get a sequence of process executions. So a schedule is basically a sequence like this. A schedule is basically a sequence like this. In this sequence, what are we saying? We want to first finish P1. Once P1 is finished, I want to start executing P3. Then I want to execute P2. I want to execute P4, so on and so forth, right? At the end of the day, this sequence, again, this sequence need not be the same sequence as this. This is a set. Here I have a set of n processes, which I can sequence or schedule in any way I want. So what does this schedule or sequence mean? This means first I'll execute P1. Once P1 finishes, I'll execute P2. Then I'll execute P3, so on and so forth, right? Imagine if I have n processes, how many such schedules are possible, right? N factorial schedules are possible. This is a very simple combinatorics problem. We have discussed such problems in discrete mathematics, right? Look at this. I have n places, right? I have n places. In the first place, I can pick any one of these n processes. In the second place, I can pick any one of the remaining n minus 1 processes. In the third place, I can pick any one of the n minus 2 processes and so on and so forth. So the total number of processes is equal to n factorial. Okay, so the total number of sequences or total number of schedules is n factorial. The total number of processes here is simply n, right? So the number of schedules the total number of possible schedules is equal to n factorial. Okay, so then there is this concept called as schedule length. Okay, so for any given schedule, for example, imagine if I have, let's take a concrete example. Imagine I have a set of P1, P2, P3. Okay, these are the three processes I have, and I said first let's finish P3, followed by P2, followed by P1. Okay, so let's assume this is my time axis. Okay, I start my P3 here, my P3 finishes here, I start my P2, P2 finishes, then I have my P1, P1 finishes here. No preemption in this case. Again, there are lots of types of schedules. This is a very simple schedule that we're talking about where there is no preemption. We're waiting for P3 to complete before we start P2. After P2 completes, then we have P1, right? So in this type of schedule, look at this. From the time I start my whole schedule, okay, if this is a timestamp 0, and if this is a timestamp, let's say 100, okay, there's something called a schedule length, which is often written as L. Okay, schedule length is the total time, to complete all the processes, in a given schedule, right? To complete all processes in a schedule. So in this case, because I started at 0 seconds and I finished at 100 seconds, my capital L, which is called the schedule length, is equal to 100 seconds, right? Again, we can also define this slightly differently. Okay, let me define schedule length mathematically also. Schedule length can be thought of as maximum of the complete times. Look at this, I have multiple complete times, right? Every process has a complete time. I'll pick the maximum complete time. In this case, the maximum complete time will correspond to process 1 minus the minimum of the start times or the arrival times. What is the minimal arrival time? Minimal arrival time will correspond to P3 because P3 is starting before everything else, right? So you can also define schedule length as the maximum complete time minus the minimum arrival time of all the processes that you have in your schedule, right? Very simple. Now, similarly, you can also define your throughput now. What is throughput? Look at this. Throughput I can also define as, look at this. If I have n processes in a given schedule, and the schedule length is n, which means it took a total of L seconds, right? Or L units of time to complete all of these processes. Can I not define my throughput as n, which is the number of process, by L, because L is time. So what does this now define? This tells me the number of processes completed per unit time, because this is the total time it took for the n processes to complete. So I can define throughput also mathematically using the schedule length. Very simple concept here. Similarly, there is a concept called as deadline. Okay, so let me define what a deadline is. So for every process, we could also define something called as a deadline. Deadline is basically a timestamp before which the process should complete. Okay, so we might say, okay, I'm starting process PI at, let's say, 10 seconds time interval, and I want the process deadline. The deadline corresponding to this is, let's say, 20 seconds, which means within this 10 seconds. So I could have again, every microprocessor has a clock attached to it. Okay, this is something that you may have learned in digital logic circuits, something that you have learned in your computer organization architecture, etc. So there is a clock associated with every microprocessor or computing device. Okay, so we can say this is when I'm starting my process. I want the deadline corresponding to this process is 20 seconds. Now, two things can happen. We could have something called as deadline overrun or underrun. Overrun basically means that the process, so given a process like this, let's assume the process did not complete by 20 seconds. So I started this. So what is my start time here? My arrival time is 10 seconds. Let's assume the complete time. Okay, so let's assume if my complete time is greater than my deadline time. Okay, if my complete time is greater than my deadline time, then what does it mean? It means, or in other words, if my complete time minus deadline time is greater than 0, then what does it mean? It means my process did not complete before the deadline given or before the deadline requested by the process. Okay, in such a case, we call it as a deadline overrun because we have overrun this time that is given. Similarly, there is a concept called as deadline underrun. Imagine if I'm completing this process, right, before the deadline, before or equal to the, actually it's precise to call it less than DI. Okay, that's a more, because we are saying underrun here, not completion on time. Okay, Ci less than Di. Basically, what does it mean? It means Ci minus Di is less than 0. Then what happens here? Then my process is completing before the deadline associated with the process. Okay, such a thing is called as underrun. Why is it called underrun? Because my process ran and completed under the time before it was given. Here it is overshot. It's called overrun because I've overshot the deadline that is given to me. Again, all these are very, very important terms. Again, so in most cases, we would want to underrun and not overrun. Because if there is a deadline associated with a process, this happens in some instances. It's better for us to actually underrun rather than overrun. Okay, very, very important. So I hope you got a good sense of some of these definitions. Again, what did we define? What did we do in here? We did not talk about any scheduling algorithms per se. We only talked about a bunch of definitions and timings and metrics that we care about. When we design and discuss a bunch of scheduling algorithms, all of these things will play an important role. That's why these definitions are very, very important in understanding CPU scheduling algorithms.